to hear what I have to tell you. This talk, I was assuming I have an audience of largely experts. And partially this is for my benefit. So this talk is going to sort of devolve as it goes on, starting with stuff I'm really comfortable with, ending with stuff I know almost nothing about. And the hope is that by answering your own questions, you can tell me the answer to those questions and advance my own understanding. All right. So what I'm really curious to tell you about today are what I'll call generalized topological, or probably more properly geometrical forces. The first part of the talk is the hard work of Xinyi Liu, who was a grad student at Harvard, and Maximilian Schemmer, who in fact was just a 6-month intern with us. And these two together did a great experiment with geometric charge pumping, and I'll tell you about that first. And then the second experiment is the hard work of Seishu Sugawa, and you'll hear about that in a little bit too. All right. So this is a whole workshop devoted to understanding the connection between quantum Hall and condensed matter systems and potential quantum Hall and cold atom systems, broadly construed. My talk in particular is focused on how the underlying topology of these systems gives rise to things you may or may not be able to call forces. The first half, you'll say that's a legitimate force because stuff moved, and I had to sell the second half as being kind of maybe a force. So topology is important in lots of quantum Hall systems. It's sort of important in a simple-minded way with the integer quantum Hall effect, in the sense that you have single particle eigenstates, and the various curvature of these eigenstates gives rise to churn numbers, and this gives rise to forces. The fractional quantum Hall effect, and I understand there were some talks about this yesterday, can also be understood in that same framework once you invoke the word of composite fermion. In any case, the idea here is that the system's periphery forms edge states, giving rise, for example, to quantized conductances or zeros in these longitudinal resistances. And this was kind of old stuff. The newer thing in condensed matter physics is there's a bunch of other systems that have ideal topology as well. For example, 1D systems that have proved quite interesting, and people like to throw around the word Majorana fermion. So in this talk, I'm going to be leading off with something that's a 1D system, and we're going to understand it, though, in the framework of 2D systems. So first, I'll tell you about geometric charge pumping. And in our system, this is going to be related to an Abelian Berry's curvature, which itself leads to the first churn number. And we're going to see some motion of stuff as a result of pumping it, and we'll understand this from the underlying geometry of band structures. The second part of my talk, this is the part that I understand less. I understand what we did pretty well, and I can explain some stuff, and hopefully you can teach me more. And this, we're going to look at a different quantity called the second churn number, or a churn class if you're a mathematician. And this is derived from the non-Abelian Berry's curvature. So we're going to be creating systems with degenerate sublevels and exploring these guys in parameter space and measuring forces, and from these forces deducing churn numbers of the second kind. All right, so this is what the framework of the talk is, and we'll just see how far this goes. All right, so the first part of the talk is what I call geometric or topological pumping. And the fundamental operating procedure of the pumps is going to be qualitatively the same as an Archimedean pump, meaning there's going to be some crank in the lab that we turn, something like this. In fact, it's be turning at a rate of maybe 500 hertz, so it's in the audio frequency. You couldn't possibly pump that fast, but it's not gigahertz. And operates on that kind of mechanical principle, but rather than just by moving stuff in that sense, it's some kind of geometric or topological property that causes the motion. And this is in stark contrast to, for example, this single electron pump, which is quantized in the sense that the electrons are quantized, but it's very much a single particle effect that has nothing to do with quantum coherence. The electrons move, they get measured, they move, they get measured. So this one is like an Archimedean pump, and we'll see how a topological or geometric pump is a little bit different. All right. So the first thing I want to expose in this talk or think about is how do atoms in lattices move? Right. So if I wanted to move something, let's say you, what would I do? I'd come up and I would either encourage you to move or I'd push on you. And one of these two things would lead to motion. But if you take atoms in an optical lattice, let's say a BEC, and it's at rest with zero crystal momentum, and you push on that system, you apply a potential gradient, at first it starts to move. It does what you think it's going to do, and the crystal momentum begins to increase. But remembering that the group velocity related to the actual motion is a derivative of this curve, you see that the block oscillation is corresponding to negative velocity when you get back here. And when the atoms return to the original crystal momentum, they've also returned to the original position in space. So taking a system of atoms in a lattice and pushing on them, yes, it leads to block oscillations, but no, it doesn't lead to aggregate motion. So Bloch oscillations, for those of you who are condensed matter people, have been done really unbelievably well in cold atom systems. So this is data from Innsbruck with cesium atoms showing not 1, 10, but rather 20,000 Bloch oscillations with a negligible decrease in contrast. That's pretty amazing. Cold atom systems can do this kind of not moving by pushing really, really well. I also like to give an example of a different case. This was taken in Marcus Griner's group here in Boston. And the difference between this and the previous experiment is they're focusing on just one atom here. That corresponds to a situation where every state in this lowest Bloch band is occupied with equal amplitude and therefore equal probability. Now when you push on the system a little bit, since each of these are occupied with equal amplitude, in fact the group velocity is, the average velocity is always zero. The thing doesn't move at all. Rather, the second moment, the width increases, but the center of mass position is totally unchanged. So it doesn't even shudder back and forth like the Bloch oscillation case. All right, so pushing on atoms, whether they be localized, whether they be bosons or fermions, as long as they're living in this lowest band, you don't push too hard, they don't go anywhere. All right, so if you want to think about forces and these quantum systems, pushing is not enough. So what we're going to be thinking about is pumping. And I invoked to you earlier the idea of an Archimedean pump. And a way you might try to realize this in atomic systems is to make a one-dimensional optical lattice, make it pretty deep, and you can argue to yourself that, well, I'm going to pin an atom in that lattice site there. Now, as long as the lattice isn't too deep, remember these atoms are going to really be sort of delocalized over many sites, and that's a key point. But intuitively what you do is you change the phase of one of the two laser fields making this standing wave in such a way that the blue curve, that's the potential, advances. You can see sort of this minimum moving in this direction, and you'd expect it to grab this atom and move it along this direction. And the simple-minded picture, though, in fact, is a little too simple-minded. It does correctly describe the situation I've sketched here, where you've localized an atom on that lattice site, but it does not correctly describe the situation for a Bose-Einstein condensate that occupies just a small number of crystal momentum states. All right? So a BEC occupies just the central crystal momentum state, is therefore necessarily delocalized over many of those lattice sites. And one can think about a thought experiment asking what would happen to such a delocalized system or system at rest in this dispersion relation if all of a sudden you had the lattice start moving. And in this thought experiment, you have a lattice that's initially at rest. It then moves for some duration of time one lattice site, and then once again stops, having moved that one lattice site. And the way to think about this, the way to ask what has really happened to the system, is imagine that you, the experimentalist, are going to stay in the frame of the lattice. Okay, so the lattice is not moving. I'm standing here. I start moving the lattice. I'm going to move with the lattice. Notice I picked a constant velocity. So once I'm in the moving frame, it's another perfectly good inertial frame. And then when I stop this motion, I stop. So a complete description of this, of my new moving lab frame experiment, is that the moment I start moving and the moment I stop moving, there's going to be a force in my description, an impulse. What that impulse does is it takes the cloud of atoms at rest and changes it by a momentum, in the crystal momentum sense of momentum, by an amount that would give rise to the velocity of the lattice. This is no surprise. But the key thing here is this dispersion relation does not have the same velocity as a free particle dispersion relation. So a particle here is moving somewhat more slowly than a particle would be had there been no lattice. So I start the lattice moving, I'm moving with it, and from my point of view, the atoms are lagging behind a little bit because our group velocity is a wee bit less than the free particle velocity that I'm undergoing. So then, after having moved one lattice site, I've moved one lattice site, the atoms have moved a little bit less, and the difference is just going to be the velocity of the lattice less the group velocity contribution. Okay. So this is not quantized motion. The lattice, they didn't move in a quantized manner. They didn't move by zero. They didn't move by one lattice site. They moved by some non-generic amount related to the actual dispersion relation of this curve. Now, if you make the lattice adequately deep, the band becomes flat, and your intuitive picture comes back. You make it sufficiently deep, the group velocity is practically zero, atoms get pinned in lattice sites, and they move. All right. But this is not a generic picture. So this idea of thinking about a situation classically can lead you awry, except in certain limits. So then how do we understand motion in lattices generically? And the way I'd like to talk about this is the framework of adiabatic charge pumping. I'm imagining, when I say adiabatic, that I'm changing parameters adequately slowly that you don't have to think about any excited bands. It's sufficient to think about just one band. But it is insufficient to think about the energies of that band alone. You need to think about the underlying wave functions as well, and how these wave functions define a geometry or a curvature for the system. All right. So here, mathematically, is the situation I'd like you to think about. Imagine I have a Hamiltonian here. This is, I'm thinking about things in a lattice, a Hamiltonian of a lattice, labeled by a crystal momentum q, and it's labeled by time t. And I'm going to insist that a period of time, capital T later, the Hamiltonian returns to itself. Okay. So I'm thinking about a time periodic drive. Now, I think that if you're an atomic physicist, I say time periodic, you think Floquet. I'm not going to talk about the Floquet description of this at all. We're going to imagine that this motion is so slow that it is adiabatic. So adiabatic, what does that mean? It means my initial state, let's say I started in a crystal momentum state Q, I undergo one such pumping operation. I've insisted it be adiabatic, so I must end up in the same crystal momentum state, psi of Q, except one can acquire a phase. And I want to think about the different kinds of phases that you could conceivably acquire in this system. All right? And in the stroboscopic sense, I'm thinking about what the system has done one pump cycle later. I'll introduce a single pump cycle time evolution operator, which you can see is nothing other than this phase where the Q here is replaced with an operator. Okay? So this describes what happens to my system after the execution of one full pump cycle. Not half a pump cycle. I can only do discrete motion in this way of thinking about it. All right. For those of you who are paying careful attention, this is really probably theorists or the experimentalists who haven't gone to sleep yet. I'm pulling the wool over your eyes a little bit with this line. But the basic idea is to say, well, given this single pump cycle evolution operator, what happens to the position operator? Right? I can think about maybe a Heisenberg picture and say, what happens to position? Well, if I simply do this commutator, remembering that Q and X are canonically conjugate, what you discover is the position operator after one pump cycle has the original position operator along with a contribution from the derivative of this phase. Okay? So I think about my time evolution of the system. I then imagine asking it how much phase a particular quantum state with crystal momentum Q acquires. All right. Now, the phase has two contributions. One of them is the one I talked about earlier. It's the dynamical phase. In other words, if you're sitting at a particular point in the dispersion relation, I'm obviously going to acquire a contribution to the phase because the energy was not zero. All right? So then I take the derivative of this phase with respect to Q by Q. Well, that derivative, what's that? That's a group velocity. So then I find that the displacement from the dynamical contribution of this is no other than the amount you'd expect given the mean group velocity over one pump cycle. That's a velocity times the time. All right? So this rather strange way of introducing a single pump cycle time evolution operator starts out by telling you something that you already knew. And it's telling you that if my lattice, if I'm sitting at a situation with non-zero velocity, I'm going to move a distance determined by that velocity in my time. Okay? So that's the first contribution to the phase. The second contribution, though, is the Berry's phase. And this Berry's phase can give an additional contribution to the motion. Oh yeah, I guess since this is bold, I should tell you about it. We're going to be thinking about situations where the dynamical contribution is zero. In the experiments I'll be describing, it'll be zero because we're sitting with the Bose condensate at the minimum of this dispersion relation, zero first derivative, zero group velocity. More generally, this would also be zero for a completely filled band, where every positive velocity v is associated with the negative velocity minus v. It averages to zero. In fact, it even averages to zero if it's not symmetric. All right, so either of these cases, a filled band or a BEC in the band minimum would have zero group velocity. But wait, there's another phase. This is the Berry's phase. And what's that phase? Well, I'm going to start here. This is the Berry's connection. And I see that the Berry's phase, if I integrate this over one pump cycle, is this quantity. So remember, I made a sort of vector potential that I'll be talking about in painful detail later on. And I've obtained what the Berry's phase is. So what this is doing is saying my state psi depends on Q and time. Interesting, that's two dimensions. I'm going to take the derivative of this guy with respect to time. How much is my state vector change in some differential amount of time? And compare that to what it was originally. Look at that overlap. I integrate that along my entire trajectory. One pump cycle, I get a phase. This is the Berry's phase. And the key thing here is that this Berry's phase can be different for different crystal momentum states. Okay? So the Berry's phase also can sometimes depend upon crystal momentum Q. And what we find then is that once you go to the description in terms of these space periodic functions, that there's an additional displacement resulting from the derivative by Q of the Berry's connection A. All right, so that's kind of neat. So now I'm looking at what's the structure of the eigenstates. And as I execute this pumping operation, as the structure of the eigenstates is changing, this too can move the atoms around. Even though the dispersion relation, it might always have zero derivative, might be completely flat, there can also be a source of velocity. Right, so let's see, what else is interesting about this slide? Importantly for the remainder of this talk, when I introduce the Berry's connection, you'll see that I've made a two-component, a two-dimensional object. One dimension is the legitimate crystal momentum. That's this component here, taking the derivative by q, looking at the q vector component. But I've made up another fictitious geometric direction with time. I have a time unit vector, and this altogether gives me a two-dimensional object.
So delta x depends on q. We have a q still floating around. So
Do I have a rogue q?
Giving the last line, there's no integral over q, so there's...
Right.
This is delta x is a function of q.
It would depend upon q. And there would be expectation values and stuff like that. We'll solve that in a second. All right, the other thing that I want to tell you about, and this is the first opportunity for me to introduce it, is in addition to having a Berry's connection, I can introduce a Berry's curvature here. One way to write this down is, in my two-dimensional case, to make it look like a magnetic field. So this looks like the z component of a magnetic field, where I've taken the curl of my two-dimensional vector potential A. Okay, so now I'm looking at a component of a magnetic field perpendicular to a surface, and here's where we're now going to start thinking about geometry and stuff like that, and topology. This surface has the topology of a torus. I'm both time periodic along that direction and crystal momentum periodic along that direction. Altogether, it's periodic boundary conditions along both directions. And now I have a two-dimensional surface where I've required a fictitious dimension of time. And my overall displacement then, if I think about the equation I had in the previous slide, I can think about expressing my derivative as a difference of two paths, like this and like this. And I find that my displacement delta x, still q dependent, is simply the integral along one such trajectory of the Berry's curvature here. Okay, so that's kind of neat. So for my Bose condensate, this is enough. I'm basically at 0q. Now the subtle point here is, of course, my system, if we measure displacements, will be a finite extent. So I'm not in an eigenstate of q. I have to integrate this over my probability distribution. More generically, though, indeed, if you have any particular probability distribution of q's, the two extreme cases being a BEC that's basically a delta function, or a filled band where each of these are occupied with equal probability, either way you get a delta x, which is the weighted average of this f of q times whatever the probability distribution is. Let's see, I don't know what I have for my next slide. The case that was originally conceived by the famous Lattices paper in condensed matter physics is the case for a Fermi gas where everything's occupied with equal probability. We're then integrating a quantity f of q, that's a magnetic field, over a surface. What's that? That's Gauss's law. We'll think about Gauss's law in a bit. What does Gauss's law do? It counts charges. So for a uniformly or system filled with equal probability, this counting of charges is going to simply tell you what's later on called the churn number. All right. It could be 0, it could be 1, it could be 2, but it can't be a half. On the other hand, if this P is something other than uniformly occupied, this integral could be anything. It just has to do with the geometry, not the overall integrated topology, the Berry's curvature. So all said and done, what you can observe is for fermions, now in cold atom experiment, both with fermionic systems or a filled band of a bosonic monoinsulator, quantized motion has now been observed. I would say this data from Munich is slightly better. If you look over one pump cycle here, the system has undergone a displacement of one lattice site there. The apparent steps in this curve result from the fact that this is a double well or bipartite lattice, and half a pump cycle later, it looks basically like it did initially. But the important thing is not the displacement from here to here, that's half a cycle, but the full cycle displacement. Okay? So that's quantized displacement because each of those crystal momentum states was occupied, in this case, with equal probability. It's a bosonic gas. Our experiments with the Bose-Einstein condensate observed a similar per cycle displacement, but now it was not quantized. It's simply sensitive to the Berry's curvature at 0 crystal momentum, which does not take on any particular geometric value. And the gray curve is what we expected by simply computing the Berry's curvature for a rather strange magnetic lattice that I'm not going to tell you about that we made today. And you can see that it agrees pretty nicely with what we measured. All right. So this is an example of where motion, in this case delta x, is derived from the changes of the underlying properties of a band structure, the underlying properties of the wave functions. And the question that I really wanted to get to with my talk today is, what was the force? And in my heart, I'm an experimentalist. And something moved because we pushed on it. And what was the pushing? What made the stuff move? So we're moving in the part of my talk now from the part where I did know what I was talking about, and we're now going to progressively fall down. I'm going to know less and less about what I'm talking about as we go. All right. So the question, the research question is, what is this force and how is it generic? Okay. This signifies my lack of understanding, going from the polished slides to what I drew in a notebook. So what I want to think about is a situation just like what I described, but I'm an atomic physicist. What's my favorite system? It's a two-level atom. And I would say 90% of physics you can understand with a two-level atom. The remaining 10% a three-level atom will do. So there's nothing important about that. Yeah. Yeah. Righto. Just recall the two-level atom, and you got a harmonic oscillator. Righto. So what I want to think about is a different kind of adiabatic process, and honestly, the one I think about most often in the laboratory, which is, a Landau-Zener avoided crossing. So to remind you, what I'm thinking of is some two-level system with a ground and excited state, and we'll make it rigorous in a second. And I imagine that I have a gap in my spectrum here with size given by omega x. And there's some parameter, I'll call that gamma, that you sweep in time from an initial value to a final value. You prepare your system in some eigenstate here, and then ramp this parameter. And the idea is, at the end, you say, well, how much is in the part of the curve which is continuously connected, having gone from spin up to spin down, and how much is in the part that's not continuously connected, that's still up. And what you find, the famous Landau-Zener problem, is that the amount of stuff that's up is exponentially suppressed for sufficiently slow ramp rates. Okay, so this is a Landau-Zener avoided crossing. And we use this all the time in the laboratory. You're in one spin state, you'd like to go to the other spin state, you turn on a control field, you sweep a magnetic field, and voila, you're in another spin state. This is how we do with our RF evaporation. This is sort of iconic in atomic physics. This is what I want to start thinking about. And here are the kind of pictures that I'd like you to think about for the system. So the first thing is in what I tell you about now, it's essential to distinguish between state space as represented by a Bloch sphere and parameter space as represented by the things you can control in your Hamiltonian. So for our two-level system, here's pretty much the complete Hamiltonian you could possibly have aside from some zero energy shift. So what you see is I have a vector of Pauli matrices, sigma x, sigma y, and sigma z, and some couplings, omega x, omega y, and omega z. And I'd like to write this just in a nice dot product form here and emphasize that this Hamiltonian H is a function of three parameters represented by the three-dimensional vector omega. So I'll sketch little pictures like this. This is representing the vector omega in parameter space. These are the parameters that we, the experimentalists, get to play with. And this Landau-Zener sweep here corresponds to fixing omega x and sweeping omega z, for example, from this point down here, moving it upwards, going there, there. Here's my avoided crossing, the length of the vector is minimum, and going back upwards again here. And the sort of intuitive idea is on the Bloch sphere now, we start in the up state, and you'd like to imagine that as this vector is going up, the state is adiabatically following until you reach here, the other pole. And of course, you didn't perfectly adiabatically follow, so the state is somewhere else. That's my psi final. But you get exponentially close to where you want it to be if you sweep adequately slowly. All right. So this is sort of, you say adiabatic, I think this. That's my atomic physics training. But I want to think about a different situation. And that's a situation where we've contrived our parameters so that the gap between these states is unchanging. It's independent of my parameter that I'm sweeping. Otherwise, a similar scenario. I have a parameter, gamma of t. We sweep it from an initial value to a final value. And the question I want to ask is how are the initial states, how does the final state relate to the initial states, subject to the constraint that the energy is unchanged? Okay. So now, can't use Landau-Zener. It's not that kind of problem. It's a different kind of problem, but it's still a two-level system. And here is where I want to emphasize this Hamiltonian, these parameters here now define a two-dimensional manifold in what was previously a three-dimensional parameter space. And when we were first doing this, I sort of conflate things in my mind, and I think about a Bloch sphere, and I kind of put on top of it the control parameter sphere. Don't conflate the control parameter space with the Bloch sphere.
Looks like a Bloch sphere.
I know it's a problem. It's round. And I think, if you have this picture of adiabatic, it follows. But don't conflate them, and we'll avoid conflation later. Right. So now, what kind of trajectory in the Bloch sphere has this kind of properties? Well, for example, if you trace on this control parameter sphere, if I trace out a circle or anything on this sphere, the energies will be unchanged. All right. And it turns out that in this case, there can still be a deflection. I mean, if you go sufficiently quickly, surely you must believe that you will be non-adiabatic, and you will, while you started in one state, you'll end up in a different state. And what you'll find in this case is that rather than being exponentially small with the rate, rather it's simply linearly small with the rate. That's really neat. So here, even if you go really slowly, you follow, but not particularly well. All right, that's really different than what we're used to with the sort of avoided crossing Landau-Zener case. And what this also means is if you want to study this kind of situation, and your bands aren't actually flat, well, if you go a little bit slower with the Landau-Zener type physics, that's going to be suppressed exponentially, and you'll be left behind with this type of physics. But what I haven't told you is, what is this type of physics? I've just already given you an answer. And I want to think about that. So this is coming back to local geometric or topological forces, the first part of my talk. And now I want to look at a little bit more detail about a really, say, a grotesque-looking symbol. I've put as many indices on something as I possibly can. There's no more room. So this is a Berry's connection like I introduced before. And in my two-level system, it's defined almost everywhere in parameter space, except at the origin where the gap in the spectrum goes to 0. Let's see. So I have a superscript n. That n is saying, well, am I looking at the ground state or the excited state in this two-level system? All right, so that's that script. You can see I'm now taking derivatives n here and there. Let's see. The mu here is what vector component of A I'm looking at. I have a three-dimensional parameter space, sigma x, sigma y, and sigma z. So my Berry's connection is living in a three-dimensional parameter space. It's a 3-vector. And that's determined here by the derivative of which component I'm taking my derivative with respect to. And that's also a function of where I am in my parameter space. It can be different at different points. So it's just like a vector field, and that's where the components come from. All right, so let's see, we did all that. All right, so in general, I can take this quantity by Berry's connection and derive from it a curvature. And I'm going to express this differently than I did before. Here it's a curvature tensor. So here's how you define the curvature tensor, f mu nu. I take the derivative of the nth component of A by r mu, subtract it from the other component. And there's another part here I don't want to think about right now. But what you see is this is no more than what I talked about the first part of my talk. I've just made a tensor out of it. This is a quantity that has components that look like a magnetic field. At least in 3 dimensions they do. And I chose a two-level atom example, not just because you can understand 80% of physics in terms of it, but in particular you can understand this bit of physics in terms of it. So this falls in that part of the 80%. So if I write down what f mu nu is in my two-level case, in terms of these components, these Berry's curvatures, as you usually think about them, they live in these off-diagonal elements of f mu nu. And they're related by this sort of anti-symmetrized relation to the components of f mu nu, if you want an equation. And the key point of everything I want to talk about today, if you remember nothing, but nothing else, remember this. This gives rise to a force in state space, not in parameter space, in state space, which is m mu, that's a force. I take a derivative of my Hamiltonian with respect to the rth component, and I find that it's simply the velocity at which my parameter is changing. This is the thing I, the experimentalist, get to turn. Turn it, that's a velocity of something, a velocity of a parameter. I take my curvature, do this sum over nu, repeated indices are summed over, and I find a generalized force. Okay, this is a force in parameter space saying that the expectation value of that particular derivative is going to change in a way that's related to the Berry's curvature. It's pretty neat. If I now think about a two-level system, remember I represented my two-level system as a sum of a sigma x, omega x, sigma x, omega y, sigma y. I take a derivative with respect to omega x, I get sigma x. These derivatives are no more than the components of the Pauli matrices. If you go through a bit of algebra, you discover in the two-level system case that this effective force is identical to the Lorentz force. Pretty neat. So in the two-level system case, we've created an effective magnetic field resulting from a Berry's curvature given my full general two-level atom example. And the force you see on the Bloch sphere in state space looks like a Lorentz force. Okay. So you explore parameter space and you see forces in state space. All right. What's the range of applicability of this idea? Well, it gives rise to the motion and the topological and geometric pumps. If you look at the equations I just expressed, you can backtrack them and find out they're exactly the same ones I talked about in the pumping. I just have to associate x with x. Of course, there's nice experiments in cold atom lattices. This is the same force that deflects trajectories if you do block oscillations in non-trivial band structures. So many people in this audience have thought about this theoretically, done experiments on it. That's legitimate stuff, okay? This is also can be thought about as the force underlying the quantum Hall effect. What makes the electrons do this and undergo motion in a flat band? Topological or geometric forces. This is a broadly applicable idea, and now we'd like to explore it in new ways with cold atom experiment. All right. So the remainder of my talk, Eric, how much time do I have?
5 + 5.
Okay, great. I can do math. That's 7. I have 7 minutes left. So we're going to talk about topology and parameter space, and it will take 5 minutes. And here's my little cartoon. All right, so we were initially inspired to do this experiment by seeing Anatoly Bakolnikov give a nice talk at JQI. He was thinking about two-level systems. And there's been some really, I want to give credit immediately in case I forget later. There have been some very sweet experiments done with two-level or even more level systems with superconducting qubits. They are going to be cited. And we were kind of sad, but then we realized you can't actually do everything with a two-level atom or even a three-level atom, so let's think about more levels. But Anatoly's idea is really the seed for what we're doing, although we've taken it a step further. All right. This is reiterating what I said before. So we're going to have a parameter space. And this parameter space is going to be littered with exactly one topological defect. Okay? And we thought about before, my two-level case, or the topological charge pumping, is a topological defect that's a Dirac monopole. It's a source of magnetic field that if you just got Maxwell's equations that said, well, Maxwell was wrong, there is a source charge, that's that kind of source, a Dirac monopole. I then reminded you of Gauss's law, that if you take such a monopole and enclose it in any enclosing surface, the integral of the magnetic field over that surface is simply going to count the number of sources on the inside. Okay, these are some generic ideas. And I said, well, in this generalized parameter space sense, that counting is giving you a quantity which in lattice settings is known as the first churn number. And that's given by this expression. Nominally, what that expression is doing, it's 2 pi is almost 4 pi. 4 pi is going to give me the area of this object. There's a factor of 2 that's sort of embedded in this curvature. So this is taking the area of pulling the area of this object out, and then looking at the average of this curvature over the surface. Okay, so this is the sort of Dirac case, and what we're going to think about then are more complicated cases. In particular, we're going to look at a system where not 1 but 2 internal degrees of freedom are relevant even to the adiabatic motion. And we're going to find a new kind of monopole that's not the source of an abelian field, but rather the source of a non-abelian gauge field. Okay, we're now sliding down the pitch of me understanding less. All right. So again, I'm taking the opportunity to tell you what I told you before, hoping that some of it sinks in a little bit. Okay, so I introduced previously the Berry's connection here, and I told you about the Berry's curvature. This is the abelian Berry's curvature. To me, something is abelian if its vector components do commute. You may remember that my original F mu nu expression had a commutator in it. They commute. That term is 0. So we can just think about the regular Berry's curvature here. And we define the first churn number, just like I showed before, as an integral over this manifold. Now, this manifold can be any manifold you choose embedded in your parameter space. Ordinarily, we think of 2 manifolds. One is a torus, because we think about 2-dimensional band structures with periodic boundary conditions. You fold it up, you get a torus. Gauss's law is happy with toruses. Or, as I showed you with my 2-level system example, it's kind of nice to think about spheres. For the remainder of the talk, toruses are kind of complicated. We're going to think about spheres. But the idea is general. We're just counting the number of quantum defects, topological defects, on the inside of that manifold. All right. So now we can go to the more generalized quantity. Imagine that we're thinking about a vector potential A, which is non-abelian. And now I need to think about those indices I told you about before slightly more carefully. Previously, I gave you what was in that case a superscript n. But more generally, you can have a n here and an m there. You can say if I had a quantum state and I move some distance in time or parameter space, how similar is it to some other state? And the idea here is we're going to have a manifold of degenerate states, and therefore it's necessary to consider all the states within that degenerate manifold. And we introduced the non-abelian Berry's curvature in this way. Now, okay, As a simple-minded experimentalist, the reason you introduce it in this way is you get the Lorentz force law back, at least in a symmetrized version. There's probably a more deep mathematical reason, but that's where this commutator is coming from. All right, and we're going to introduce another quantity. There's an idea in topology and mathematics called churn classes. And we're going to now look at the second churn number. A really interesting feature of this is the first churn number can only be non-zero when time reversal symmetry is broken, but not so the second churn number. So we are therefore now going to construct an experimental system in which time reversal symmetry is not broken. The first churn number will vanish, but we will measure the second churn number. All right, so given that I'm on my question time, right?
You're into your question time. Time to introduce your experiment.
Yeah. So we're going to do that. All right. So here's what we're going to do. We're going to work with 4 cyclically coupled levels in the F equals 1 and F equals 2 ground state manifolds for rubidium 87. I, as an experimentalist, call these blue ones microwave transitions, and I call those red ones RF transitions. It doesn't matter. We can control the amplitude and phase of these things extremely well independently. Now we have a 4-level system rather than a 2-level system. I'm going to have an incomplete representation of that 4-level system in terms of a sum of these Dirac gamma matrices. And we're going to pick this just like Pauli matrices, except there's more of them and they're 4 by 4. Right? And we're going to select the parameters R1 through R5 in such a way that the energies don't depend upon my parameter choices. So now I have a 5-dimensional parameter space and I'm embedding a 4-dimensional surface, 4-dimensional hypersphere, into that parameter space. And we will select our parameters such that in my parameter space I will have a pair of degenerate states here and here forming my ground state manifold, and a pair of degenerate states here and here forming my excited state manifold. And I will sweep about in parameter space in such a way that these always stay degenerate and always keep the same energy. That means at every point in parameter space we have the freedom to explore a Bloch sphere which is defined by those 2 local eigenstates. So now, rather than thinking about phases, I have to think about matrices. And it's these matrices that, in fact, are the origin of the force we measure. Okay. We do full quantum state tomography to be able to measure the full quantum state after our experiment. And here's the type of things that we do. This is my control parameter space. In the center of my control parameter space is a defect, a 0, a singularity, in my non-Abelian Barry's curvature. We then sweep out circles, or other shapes, but always, in fact, always circles in this case in our parameter space, and measure, in this particular case, all the components of these different Dirac matrices. We measure all the expectation values. The red curve is what you would have measured had we been adiabatic. The blue curve is the prediction of slight deviations from adiabaticity, and you can see the little dots are the experimental measurements. So we've done quantum state tomography. Using the tomographic data, we've gone back and figured out what the expectation values of the Dirac matrices are. Again, to emphasize, in terms of a state space representation, each point in state space here is still associated with the Bloch sphere, some internal degenerate manifold. Okay, so state space is bigger than it was before. What do we do then? Well, we sweep out some trajectory with the differing degrees of non-adiabaticity. Why are we doing this? Remember, I showed you a relationship between a generalized force and the underlying curvatures. We measure the result of that force. That force is giving rise to these oscillations. This plot is showing you all the components of the various different, this is one is showing one component of the gamma matrices for different initial states on my Bloch sphere, which is now in this degenerate manifold. We measure different curvatures. This is the theory. This is the experiment. We get Eric to stand up. We also change the ramp rate to make sure that we're in this linear regime.
Is that reversible?
Well, let's find out. I go back a slide. Okay, it is. It's adiabatic. And we measure, we verify indeed that we're entering into this linear regime and this linear response regime where indeed we're measuring this generalized force. And from this generalized force, we can finally obtain the second churn number. So what this plot is showing here is a measurement of the second churn number. But wait, it's not quantized. What we're doing here, what are we changing? We're taking this sphere and parameter space, and now we're moving it. Different experiments with different centers of the sphere and parameter space, such that the source of non-Abelian curvature, this Yang-Mill monopole, is ultimately outside my parameter space. And as you might expect from the intuition about charges, this churn number, or this integral over this surface, goes from being 1 to being 0. Why is it not quantized here? It's not quantized because we're leaving the range of the linear response theory in this region here. So the simulations are for more and more slow ramps, showing that, yes, it will become steep in more and more linear response. And we can also measure the first churn number, and we find that indeed within the experimental noise, this first churn number is 0. That's what we expected. It's a time reversal symmetry preserving system. With a non-zero second churn number, there is a topological transition, but it's one that could even exist at zero magnetic field in a condensed matter system. So these are our measurements of the second churn number, and you can see that one is 0. And I think that's the end of the slide. So the last sort of thing we can do that I haven't talked about is we can measure things called Wilson loops, which is sort of like the Berry's phase as you sweep about even perfectly adiabatically in this parameter space. Now we'll end here.
Question. Could all these experiments in principle, they can all be done with a single atom? Yes, just many iterations.
Absolutely.
And there's no, if what I think of as space, which is this three-dimensional coordinate space, there's no space dependence. These experiments. This is done in uniform radio wave fields.
Yeah, that's right. So just to make sure that everyone heard that. So these experiments were performed with a Bose-Einstein condensate, or a great many of them, maybe 10,000 of them, each one located in series, one after the other, of course, with about 100,000 atoms in a crossed optical dipole trap. These 100,000 atoms just gave a signal to noise. So we're exploring an internal parameter space, defining a 5-dimensional space on which we have a 4-dimensional manifold.
We have time for maybe one more question.
Your ground state, the day you're operating on is a pair of degenerate states.
Yeah.
And that's all there is. And then what's the next excited states? Is the separation from them?
Okay. I think I had the numbers in different slides. So I'll give you the ratio because I happen to know that. This is experiment, so these are not exactly degenerate. The difference in their degeneracy is about 0.5% of the gap between these things. Now, the order of magnitude of the gap is about 3 kilohertz. Well, order of magnitude is kilohertz. I think it's 3. So we have maybe 10 hertz gap between those guys, kilohertz gap between those guys.